Guys, I apologize about Monday. I wish I had a better story, like I was fighting in a bar or something like that, but I was fighting with a small toy table and I lost. So yeah, don't do that ever. It's been painful. So I'll be moving around like Robocop today probably, because I'm really scared, but I'm doing better. So I really hate giving you videos from last year, but I didn't see any other solution. So I hope you all watched that video that introduces interplanetary trajectories. The bottom line is that we're doing preliminary trajectories, which means from, for example, a circular orbit of planet 1, or call it home planet, to a circular orbit of planet 2 or target planet. All we do is, assuming that we leave, so this is the sun, this is planet 1 orbit, we leave this planet, we go on a Hohmann transfer that is only influenced by the sun, and so we leave the sphere of influence of this planet, which we have to compute today. Once we are outside of that, we only see the attraction of the sun for all this trajectory here. And then here, eventually, hopefully, we'll meet the second planet, P2, and we enter its sphere of influence. So we use what we call the patched conics method, which means you're patching conics. Inside the sphere of influence of planet 1, you don't see anything else, so you do everything that we have done so far. Of course, you want to leave that, which means you have to go on a hyperbolic path that eventually will lead you outside of this imaginary sphere of influence. And once you are outside of that, you're just going on this Hohmann transfer, and you invert the transition once you get to planet 2. So the video that I gave you should have stopped at the point of basically doing this, computing, timing these maneuvers. If we're doing a 2-impulse burn, and let's assume that once and for all this is Earth, and maybe this is Mars, because everybody is talking about this these days, and that's most of the problems that you have on your book have Mars and Earth. So we were dealing with the phase angles, how these planets have to be positioned with respect to each other so that you can do this. So in the previous video you have, the discussion about what this phi 0 has to be once you have radius of the first planet's orbit, r1, and r2, which also mean that you have their angular velocities. These are all circular orbits. So you can compute what this needs to be so that once you leave planet 1 and you travel on this half ellipse and you spend a time t12 on this half ellipse, so that P2 is going to be actually at the apogee of the transfer, right? So that's a simple angles exercise that you should have seen in that video. And I believe there's also discussion about how often you actually see the right phase angle to do a Hohmann transfer from 1 to 2, and I believe between Earth and Mars is about 2+ years. So that's how often you can have the right configuration, like in this case, for phi 0, so that they actually, your spacecraft is actually going to meet Mars at the other side of the ellipse, right? So if you miss the window, you wait for this kind of maneuver, of course. It's not the only one, but it's an impulsive, the most efficient one. You have to wait more than 2 years. Yes?
Would that have you crashing into the planet, or
no.
Starting to rotate it?
No. So these kind of, again, these are patch conics. So if I zoom in, for example, around P1, what is actually happening before I leave the sphere of influence is that, and again, P1 is my planet Earth, I have this imaginary volume around the planet. We'll compute its radius today. And inside that volume, I can assume that the only attraction that I experience is the Earth. I don't care about the sun, I don't care about the moon, it's an approximation, but that's all I see. So what you're actually doing here is that, say that you're, and we'll see these in the next lecture actually, say that you're on a circular orbit around the Earth, and at some point you're ready, you time this correctly, you need to get out and go on the transfer ellipse. Well, then you're going to probably burn here so that you go on a hyperbolic path with the right asymptote that leads you at the edge of the sphere of influence with some residual velocity that is sufficient so that you sum this up to the velocity of Earth, and now you go outside, and from the sun's perspective, here you're going to have v infinity, this is the velocity v infinity, plus v of the Earth. Because remember, everything we've done so far is relative to the planet. So if I am inside the sphere of influence of the planet, everything that I'm doing is relative to this planet, and this planet is also traveling with respect to the sun. So this planet has its own velocity. So what you're doing here is you are burning here so that you go on the right hyperbolic path such that the excess velocity adds up to this, and you have the right perigee velocity with respect to the sun. That's why it's called patch conics, because it's not actually what happens. I mean, you are always under the influence of the sun as well, but here I'm just saying, hey, when I reach this distance here, I forget about the Earth, and all of a sudden all I see is the sun. It's a rough approximation, but it gives me an idea of the delta V's that are involved. Yes?
So in that sphere, we just worry about the full force of gravity from the Earth.
Yep.
Out there, we just worry about the full force of gravity.
Right. So if you have to look at all the equations that we've seen inside the sphere of influence, right here, you only care about using the mu of the Earth, right? Once you leave this thing, all the equations that you're going to use only have the mu of the sun, until on the other end, this is Mars. It's going to have its own sphere of influence, which is a little smaller than Earth's because it's a function of the mass, as we'll see. And so here you're actually coming in with some velocity that will be your v infinity, but now you're coming in with that velocity. It's a different one. This is whatever that is. And you're coming in with this hyperbolic path that if you don't do anything, you're actually going to exit on the other side. But obviously, if you want to remain there, you will have to slow down and go into some circular elliptical orbit around Mars. So this is the idea of patch conics. I do something around the first planet so that I have enough v infinity to leave its sphere of influence, and I will add that velocity to the inertial velocity of the planet with respect to the sun, and that gives me the total. We'll see this next time. But that is the idea. That gives me the total velocity that is enough to go on this half ellipse that is only based on mu s, basically, on the attraction of the sun, until I get close enough to Mars that I'm actually switching to its sphere of influence. So you don't care about, basically, you're still doing single attracting body kind of astrodynamics. You don't do two at the same time. That is the approximation that it's used. Make sense?
Is this approximation good enough for actual orbits, or is that just...
It gives you a ballpark number for the delta V's that you have to use. That's basically the idea. Yeah. Then if you have to do it precisely, you definitely have to have some software that takes into account, like the SPICE toolkit that Patrick discussed, that actually takes into account the gravitational attraction of all planets at the same time. But, you know, if you look at the what happens in low Earth orbit, the attraction of Moon and Sun, as we have seen, they're really negligible with respect to J2 and drag, for example. So it really depends on distances. Of course, as you get closer and closer to this imaginary edge of the sphere of influence, the approximation that you only see the Earth as the attracting body, it's losing its power. Because the Earth becomes smaller and smaller, you're going away, and you probably start experiencing the attraction of other objects. The Sun, if you look at the masses of the planets in our solar system, the Sun is, I want to say, 3 orders of magnitude or more massive than Jupiter, which is probably 3 orders of magnitude more massive than the Earth. So the Sun is dominating everything. So it's of course an approximation that loses its power when you leave all these smaller objects around the planets. But it is used. It is used for ballpark numbers in terms of delta V's. So what I needed to finish, though, is, well, we know that the correct phi 0 to transfer on this half ellipse is every 2+ years. Now, imagine that you have reached Mars. Somehow you slow down, you remain, you land on Mars, you do whatever you have to do, and then you want to come back. First of all, if I just wanted to reach Mars and come back right away, you can't just, remain on this ellipse and hope that planet 1 is going to be right there, of course. Because what happens is that planet 1, and I didn't bring my computer because I didn't want to carry a backpack, basically, but think about this. The planet 1 is on a smaller circle, so that means it's moving faster around the sun. by the time the spacecraft has reached Mars, in this position, planet 1 would be somewhere here. It will be ahead of planet 2 in terms of phase angle. In particular, if you look at the equation for the phase angle, I think this is also the end of that video, you can easily compute that the final phase angle, so at the end of that T12 transfer ellipse, the actual phase angle between the two planets is pi minus n1 T12, where n1 is the angular velocity of the Earth around the Sun, in this case, if P1 is the Earth. So you can easily prove to yourself that this is actually negative, which means, by the way, I have defined the phase angle, which is the angle of, so this is my line of reference to measure angles, right? The phase angle that we defined is the angle of P2 minus the angle of P1. So if that's negative, it means that planet 1 is ahead of planet 2, right? How do you prove that? Well, again, think about what you have. T12 is half orbital period on that ellipse. That has the same major axis, which is bigger than the same major axis of planet 1's orbit, which is R1. So you can easily see that this is bigger than pi. Anyways, it is negative. So what do I want in terms of the next phase angle? Well, I want to know when I'm good to actually leave Mars, basically run the same exact ellipse, just the other half if you want. Of course, it will be somewhere down here. It's not going to happen right away, but the sketch is still valid. You're going to run this other ellipse, half ellipse, and have planet 1 at the right location. And the time of flight is the same, right? I'm using the same kind of ellipse, right? This is to get there, and this is to come back. So what has planet 1 done? Well, in planet 1, if I redraw my line to measure angles, and this is the can draw circles, of course. This is my circular orbit of planet 1. I left from here. So let's say this is P1 prime, at the moment of doing the first delta V, going on the ellipse to transfer. So it will travel on its path, and then it will end up somewhere here where this angle is my new phi final, right? Because this is where I want planet 2 to be at the end of the transfer. So this is planet 2 second at the end of the transfer, and this is planet 1 second at the end of the transfer. Does it make sense? If you want, I can draw also the bigger circle here, because planet 2 is actually not here. Yeah, it's somewhere else here. So, yeah, on the bigger circle, right? Bless you. So, and this was planet 2 at the beginning of the transfer was here. It travels slower than planet 1 on its orbit, and it ends up here. And in the meantime, planet 1 goes from here to some position down here that is ahead of 2, given by this angle, right? So what I want is basically to find my planets in a new initial phase angle so that planet 1 can travel another pi plus phi final, right? It has to cover the same distance on that circle. In other words, you need to wait for a new, call it initial phase angle. I'm calling it phi 0 prime, and that needs to be minus phi final. Does it make sense? What I had there was actually planet 2 being ahead, right? So I need to wait enough time so that these two objects find themselves in a configuration where planet 2 is ahead again. Otherwise, the moment I leave it, I cannot expect planet 1 to be where it needs to be. Can we see that? All right. If that's what I want, then I go back to my phase angle equation that was, the general equation was phi as a function of time. Now my new initial condition now is phi final, because I'm starting to count from there, plus n2 minus n1 t. This is something you should have seen in the video. But I know that I want to find the time, the right time, so that that phi becomes minus phi final. So I'm going to substitute this in my desired angle, so I get plus n2 minus n1 t. So now you have an equation where I know what this is, by the way. I can always plug it in. I can do it later. I have an equation where I can solve for my wait time. So again, what I want to find here is after I leave, I have left planet 1, I've gone on this ellipse, this is the time where I reach planet 2, I reset the clock right there, so that's my new 0, right? I start counting time from there, that's what I'm doing. So from that point on, I want to know how much I have to wait so that the planets are in a configuration where I can run a similar half ellipse, it's identical basically, and find planet 1 at the other end. Okay? So t wait here, if you plug in everything that we have, is going to be, of course, minus 2 phi final over, so minus here, n2 minus n1. And if you want to generalize, I don't think I need to cancel that. In general, so that is the shortest wait. But in general, you can say that your wait time to come back home, basically, is minus 2, whatever your phi final is, which depends on angular velocity of first planet and time of flight to the transfer, minus 2 pi n, where n is an integer, divided by n2 minus n1. And this is, again, we're doing the case where n1 is greater than n2 without loss of generality. You can do the opposite. So this is how much you have to wait. You can wait just this or longer. Every 2 pi times n, you're going to have the planets in the right configuration so that you can return. I think there is an exercise or example in your book, I believe is 8.2, where this is computed, so that one down there actually, the shortest wait time is computed between Mars and Earth again. So they are telling you how much you have to wait so that you can leave Mars and come back. And if I'm not mistaken, I think it's more than a year. It's 400 something days. So if you put all these together, you basically, with the Hohmann transfer from Earth to Mars, you wait for the right phi 0 to occur, and that happens only more than 2 years. So you need to know when you can do it. Then you travel on this ellipse, which I think is done in a previous problem from Monday. I'm not sure what is the travel time. It's pretty long. It's more than a year as well, if I'm not mistaken. And then you can't just come back. Of course, why would you want to come back? If you're sending a mission to do something there and you have to come back for some reason, maybe there are humans, of course you're not going to come back right away. But the minimum wait time is more than a year, and then you have the travel back. So you can imagine, you're talking about multiple years in space, which is, so far, is a problem. For humans, at least, it's a problem. But this, of course, this is a Hohmann two-impulse burn. If you have more powerful engines, you can do different things. You could, no one is telling us that you cannot do something like this, where you leave planet 1 and just go almost in a straight line to planet 2, and you intersect it here, where the time of flight can be a lot shorter. But that is a function of powerful engines. Do we have enough powerful engines? Because the delta V's that you're talking about here take definitely more than half of your weight just to get there. So you may not even have the right technology to come back. So yeah, it's expensive maneuvers, that's for sure. Was there a question? No?
What's N2 and N1?
Oh, N2 and N1? Oh, and N1 is, it's basically omega 1 is the angular velocity of planet 1 around the sun, and N2 is omega 2. Yeah. Proportional to the orbital period of the planets around the sun. Yeah.
What's the capital one?
Capital. Oh, this is an integer. So this is 0, 1, 2, 3, etc. Yeah. Because this is all periodic, right? Everything repeats itself as a function of the difference between these two. They are just circular orbits. One is bigger, one is smaller. So everything that is happening repeats itself all the time, but it's just a matter of waiting, because these are, our orbit around the sun is, 365 days or so. Mars is a little longer, but not that much longer. So the difference between these two angular velocities is not that big, so that's why you have all these wait times. Because before you find the phase angle that aligns with the last condition, the same exact condition, you're going to wait for a long time. Make sense? So we'll go more into the details of these, what happens here so that I can create the right velocity and then go on the transfer one, and then what happens at the target planet. But this is, the Interplanetary Trajectory 101, where you need to time these maneuvers correctly, and you need to know what are the times involved. And this is for the Hohmann transfer, which is something that we have seen before, so it makes sense to do it that way. Now, what is this sphere of influence, though? I think it's time to define it. It is some imaginary volume that we define around the planet, where we say, okay, inside this volume, I really care about only the attraction of the planet, and after that, then it's the sun. But there is a way to compute it. So let's say that we're looking at sun. MS is the sun. I have my planet somewhere else, MP, and I have my spacecraft somewhere else. And I just say that this has a mass, just M. And I'm going to call big RS the vector sun to spacecraft, little r the vector, as we've done so far, planet to spacecraft. This is the one we've been dealing with for the entire semester. And then simply big R, the vector goes from sun to the planet. So I claim that I am inside this SOI, or sphere of influence, if the following happens. Let's see how I call them. I call them perturbations and accelerations, yeah. I'm going to explain what these are in a second. PS over AP is less than PP over AS, where by P I mean perturbation. They're all accelerations here, but when I say P, I am looking at a perturbation. When I say A, I'm talking about a main acceleration. So what I'm saying is that I am inside the sphere of influence of the planet, P, if the ratio between the acceleration on the spacecraft due to the sun over the acceleration due to the planet is less than the perturbation due to the planet over the acceleration due to the sun. Does that make sense? So basically, you are inside the sphere of influence if the sun is a perturbation, is less than what you experience because of the planet, and vice versa. You are outside of it if the sun takes over, which makes sense. So that's exactly the expression that I'm going to base everything on at the end. But I need to compute the second time derivatives, basically, of all these vectors here that are involved, and do some simplifications. Always keep in mind that the sun is a lot more massive than any planet in our solar system, which means that most likely the sphere of influence of these planets will be tiny compared to the distances between planet and sun. So at some point I will make the approximation, not for now, that, for example, R and RS are more or less the same thing. That this vector here to the spacecraft, if I am inside the sphere of influence, of course, it's probably tiny. So you're sitting on the sun, you're looking at planet Earth, for example, and a spacecraft that is orbiting Earth and it's inside this sphere of influence, you're probably not going to even notice the size of this little r that is changing. Make sense? If it's inside the sphere of influence. If it's traveling to another planet, then it's a different story, but then you're not inside the sphere of influence anymore. So, but we'll use that as the main approximation, and then, of course, it's obvious that the mass of the spacecraft is going to be definitely much smaller than the mass of the planet. We use that at some point, and even more with respect to the sun. But let's write a few forces here. So the force on the satellite due to the planet is, as we know, minus g m of the planet, little r cubed r. That's the one we've been using all the time. The force on the satellite due to the sun is instead minus g m mass of the sun. What is that? That's rs cubed as well, times rs as a vector. And finally, fsp. Be careful how much I bend, I'm sorry. By FSP, I mean the force that the sun is exerting on the planet is minus g m of the planet, m of the sun, over r cubed, big R vector. Okay. So let's start from rs. Double dot. So I know that m rs double dot is equal to what? What is this? Now the sun for me becomes the inertial reference frame probably, right? So this is all the forces acting on the spacecraft, which is sun plus planet, which is minus g m of the planet over r cubed times r minus g m of the sun over rs cubed rs vector. So I can definitely, simplify this and just look at rs double dot, which is given by these two terms. Let's see. This is going to be divided by m, of course. This is almost equal if I start using these assumptions here. Again, I am inside the sphere of influence. I want to compute the radius of the sphere of influence. I have minus g m of the planet over r cubed r minus g m mass of the sun over, so this just becomes r, right? If I assume that this is true. Okay. And I'm going to call this and this what? I need to find something to plug into this expression, okay? Because that is the one that will give me my sphere of influence radius eventually. So I have two of these elements here. Which ones? What do you think? This is more or less the acceleration due to the sun, right, on the spacecraft. And this is, in this case, I call it the perturbation due to the planet on the spacecraft. Okay? And so I can do the P over AS. And I'm going to copy it there in a second. So I'm just looking at the norms. P over AS, let's see, is G m planet over little r cubed r, which divides G m sun over r cubed big R. Simplify a few things here. You are left with m planet over m sun big R over little r squared. So I'm going to actually substitute that in this expression right here. let's see, mp over ms big R over little r squared. So eventually from this expression I need to substitute something here. I will solve for little r, and that will be my radius of the sphere of influence, okay? And you can start seeing that all I want to see appearing here are masses of the planet and sun, of course, and the distance between the planet and the sun, which makes sense. Because probably if you're closer to the sun, your sphere of influence is going to suffer. It's going to become smaller. It's easier to get attracted by the sun, right? Okay, so that is the first piece, or second piece of this inequality. And then we'll do something else. Let's see, what do we do? I'm going to look at the planet for a second. MP R double dot is equal to, in principle, the planet is attracted by the sun and the spacecraft. Of course, what the spacecraft does to the planet is kind of ridiculous, but we're going to have it there for a second. So this is actually the FSP that I wrote down there, minus actually the what did I call it? FP, right? So this is, let's see, G, what is FSP? Minus G ms mp over, that's r, big R cubed r. And then I have minus, right? Yeah, plus gm, m of the planet, little r cubed r. All right. I'm going to do the same I did the other with the other equation. Divide by the mass, divide by the mass, divide by the mass, and that's what I have. Gm over r cubed little r minus gms big R cubed r. That's fine. Now with this, I'm going to put together the little r double dot vector, which is big R double dot s minus big R double dot, which I have. I have both of them. I have this expression here before I simplified it, and then I have this expression here, so I can just subtract the two. Let's just write them as they are for a second. I have minus g mass of the planet over r cubed r with a little r minus g ms. I'm going to keep using rs for a second, and then I will simplify at the end. So this is rs double dot minus all this, minus gm over r cubed r, and plus gms over r cubed r. Okay? Is this making sense? Yes?
But I have a question. To the right, when you cancel the ms, how did you cancel that because you're dividing by n?
Yeah, no, it's not cancelled. Thank you. Thank you. No, I think there is, hold on. Hold on a minute. One has to go. This was okay. This was okay. Was it okay in the first place? I think it was right. Does it make sense? So, let's do this again.
Sorry, that's what I'm just asking. I don't understand.
Yeah. So, this is FSP, right? If it's correct, that is the force that the planet experiences because of the sun. So that has to be mass of the planet, mass of the sun. And so we have them there. And when I simplify with the mass of the planet, that becomes an ms, and that's right here. And this is spacecraft, so it should be okay.
Oh, okay.
Right? Yeah, I mean, that will pretty much disappear at some point, but that the second force, once I divide by the mass, it's an acceleration, is this one here, and it's what the planet experiences because of the spacecraft.
Okay.
I will get rid of it, but yeah. Anything else?
So you don't need that S now?
I do not. Yes. Thank you. Let's collect a few things together here. I like this one and this one. They can go together somehow, and this should become, let's see what I have here. Yeah, I have a minus g mass of the planet over r cubed, little r that multiplies 1 plus mass of the spacecraft over mass of the planet. As you can imagine, this will just disappear because MP is much bigger than M. And then I have minus, I like these two together because they have GMS, GMS over, let's see what we can do. We can do different things, but let's collect these. RS cubed that multiplies RS minus, let's make it a square bracket here, simply RS over R cubed R, right? These two terms. Make sense? I'm going to move all the way down here. No, here. Okay. So let's manipulate that a little more. I have minus G mass of the planet over b little r cubed r 1 plus m over mp. That has not changed. But then I have g ms over rs cubed. I have a few more parentheses here. So you can add and subtract big R. And so you can make little r appear here, but then you have this correction. 1 minus rs over r cubed that multiplies big R. Make sense what I've done here? Little r again is, well, aside from the double dots, little r is rs minus r. So if inside these parentheses I subtract a big R, I have to add back a big R. So this is what comes out of subtracting, and this is the additional big R. Now I can make my simplifications. Right there. This goes away. This is about 0 pretty much. If RS and R, this is not a vector, if RS and R are comparable, because I'm definitely inside the sphere of influence, that's what I'm looking for, this becomes a 1. This goes away. At the end of the day, I should see something that looks like minus G MP over little r cubed times r vector minus G ms. Again, at this point, rs and r, the two R, the capital R's are the same thing. So I have big R cubed R. That's a little bit of algebra. Now, at this point, I'm going to call, bless you, these two pieces. Well, this is now the acceleration due to the planet that I need there. And this is the perturbation due to the sun. Yes?
Excuse me, why is that the big R vector instead of the little r vector on the right there?
I use the two assumptions.
But it's the little r vector up there. See?
It is. Thank you. That's right. So is the line of thinking clear? This is the starting point. And that's why I started from this, this first ratio gave me perturbation due to the planet over acceleration due to the sun. That's why to compute this one, I started from looking at this acceleration. Like my spacecraft is mainly orbiting because of the sun. And the Earth or the planet is a perturbation. It's something that is annoying me, right? So that's how I get this ratio. While this other one is the opposite. That's why I started from this vector here, which is the usual one we use in astrodynamics for orbiting around the planet. Make sense? Okay. Well, I have to compute this ratio now. So what is PS over AP? let's see what we get. PS G ms over r cubed r over G m planet over simply r squared, which in the end gives you ms over m planet, little r over big R, this time is cubed. Now if you're asking yourself, this is squared, that's cubed, that's fine. That's ratio of two distances, so these ratios are dimensionless. So it still works. So that's what I want to substitute in here. ms over mp, little r over big R cubed. And now I have my inequality that I'm going to solve in terms of the little r, because that will be my sphere of influence around this object that satisfies this inequality. If the inequality doesn't hold anymore, then I say that I'm outside the sphere of influence. So that's an additional step, which we can do down here. All right, so I have ms over mp little r over big R cubed has to be less than mp over ms big R over little r squared. So in the end I have this expression on the left, little r over big R to the fifth has to be less than m planet over m sun squared. Yep. And so if you want, you can say the radius of the sphere of influence over the distance between planet and sun has to be less than mp over ms to the 2 over 5, and that's the end of the story. Or if you want to multiply times r, but that's how you get it. So if you're given a planet, you know its mass, you know more or less the radius of the orbit around the sun, you know the mass of the sun, this is how you compute your sphere of influence. Questions? Is the procedure logical? Make sense? Again, this is all an approximation. Of course, you are subject to everything at the same time, but it's a matter of how much, what is dominating. Now, as an example, the sphere of influence of the Earth, I'm not going to give it to you as a number, I'll just give it in perspective of the radius of the planet, is 145 times, more or less, the average radius of the Earth. Times. This was 6,000 plus kilometers. So the sphere of influence of the planet is 45 times that, which obviously means, can I say that the moon is outside the sphere of influence? Of course not. It wouldn't make any sense. The moon is orbiting the Earth. It better be inside the sphere of influence. So definitely doesn't apply this approximation to the moon. So if we're flying to the moon, we can't do this patch conics business. You definitely cannot do that. I have a few more numbers. Just to put it in perspective, the distance, so this would be the big R. The big R for the Earth, right? The distance to the sun is 23,460 times, more or less, the radius of the planet itself. And that is what I expected. The distance between the planet and the sun is probably going to be much, much bigger than this sphere of influence that I wanted to compute. This is these are right here. Make sense? Look at this, planet over sun. So if you're guessing, how is it possible that this number, which is a lot smaller than this, is coming from here? It is possible. Big R is a lot larger than the sphere of influence, but there is this ratio here, so everything makes sense. The mass of the Earth is a lot smaller than the mass of the Sun. Several orders of magnitude. Questions? Concerns? Issues with these?
I would say radius of the Earth is only 3,000 times the radius of the Earth.
Sorry. That's the one. So we've seen the timing, the idea between the patch conics, sphere of influence, Sun, another sphere of influence, the timing issue if you assume that the orbits of the planets are circular, how often you can do a Hohmann transfer, how long you have to wait